So we're going to look at behavior of functions, and a lot of it's going to be related to what is happening, what is the behavior on the graph. Okay, so we need to define a few terms, and then we will start looking at functions. So when we are talking about the domain of a function, in the past, you have probably been told that those are the x values, the x's. So for domain, we are talking about input values, because functions don't always have to be written in terms of x and y. Okay, but in our domain is input values where the function is defined. So any values for x that you plug into the function and you get a numerical answer out. There are some functions that are not defined for all values. So to find the domain, what you want to look for is where the function is undefined. And at this moment in time, we have two major places where a function is going to be undefined. The first one is if we are asked to take the square root of something that involves variables. Let's just say the square root of some stuff, okay? We are only able, with real numbers, to take the square root of positive numbers or 0. So that means the domain for that is going to be defined wherever what's underneath the square root is either positive or 0. We can take the square root of 0 and we can take the square root of positive numbers, but what is underneath the square root cannot be negative. The other place where we tend to find undefined values is when we have fractions. Anything on the top or something on the top, we do not want 0 over 0. But whatever the stuff is in the denominator, that cannot equal 0. We cannot divide by 0. So when I have a function and I'm asked to find the domain, what we're actually really looking for are any exclusions from the domain. Any place where the function would not be defined, everywhere else is part of the domain. Anywhere the function is not defined is not in the domain of the function. Range is usually, you've probably been told, the y values. But again, we don't always write it in terms of x and y. We can write relationships or functions in terms of other variables. So to be more specific, we are talking where the outputs are. We're looking at the outputs that can occur and usually at this point, calculus, we use calculus to find the range. Mathematically, we are going to be visually stating the domain from a graph. We are not going to be algebraically finding the range in precalculus. You do in find the domain algebraically in precalc, but for range, we will mostly be looking at the graph. So when I look at this example of a graph here, and notice that I have a filled in circle on this end and I have an open circle on that end, that means that my domain is going to be where the function is defined, which x values give me y values. So in this function, the domain is going to be x is greater than or equal to -4, because -4 has the closed-in circle, you can actually get a value at -4, but only less than +3, because at +3 we see that open circle. I should change these. So -4, and then I'll pick a different color. We see an open circle, so it is not equal to 3. We are going to come back to this in a minute, and we're going to look at another way to write this that doesn't involve inequality symbols. The range, I should have done domain in purple, because that was the color I set up there. Let's switch that. And then the range was in blue. So for my range, now we are only looking at the Y values. And with this one, let's look at the lower level first. So my lowest Y value is -5, and it is not an open circle at the -5. So you can see here, when I look at my range, I looked at my domain, filled in circle, open circle, but here the function actually takes on that value. So it is an equal to, and then here, it is also an equal to, because even though it is an open circle at this point, the function does take on that value at the other point. So my range is going to be less than or equal to 5. All Y values between -5 and +5 can occur. That's how we see the range on this, okay? Now, we also, one of the things when we're talking about the behavior of a function is we need to talk about where is the function increasing, where is the function decreasing, where is the function constant, what intervals does the function have these behaviors happening. So this is really pretty intuitive if you are looking at a graph. If you would like to try to just see if, without me even defining it, where is the function increasing, where is it decreasing, where is it constant, go ahead and pause the video and try that. See if you can come up with those. So a function is increasing, whereas I move from left to right, we see that it is going up. So that function is increasing there. The next place the function is increasing is in this section right here, because it is again moving up the page as I go from left to right. And then the last place the function is increasing is here at the end. I mean, increasing means as my X values get bigger, my Y values get bigger. Decreasing is going to be as my X values get larger, my Y values get smaller, decrease. So the function is decreasing on that interval. It is decreasing again on that interval. And those are the only two places where as my X value gets larger, my function value gets smaller. And then constant intervals, where does the function value remain constant, where it doesn't change? So that would be here. So if I was looking at looking at my intervals, I can state where the function is increasing, where it is decreasing, and where it is constant. Now, what we want to do is we want to use interval notation for our description of the domain and the range. I believe this is how you would have done it in Algebra 2. And for increasing, decreasing, and constant intervals. So we're going to look at function or interval notation, and then we're going to go back and state increasing, decreasing, constant, range, domain using interval notation. So for interval notation, if the boundary is not equal to, so in this example for our domain, that's where we had the open circle. It is approaching, but it doesn't actually ever take on a value there. We are going to use a parenthesis. So that would be when x is less than some number, or when x is greater than some number, okay, that we're going to use a parenthesis if it does not say or equal to. Then if the boundary is equal to, we're going to use a bracket. So that would be in the case where x is less than or equal to some number, or when we're talking x is greater than or equal to some number. And then between these, we are going to be talking about a union. Now, because I write the word union with a capital U, this is the or. The domain is this interval or this interval, because the value can't be in both intervals at the same time. That's the definition of a union. We are going to use this symbol. It is not a capital U. Do not put the tail on the U. If you do that, I'm going to be marking you down. That's not the correct notation. It is a union symbol, which is just that U without the tail. Okay, so if I go back up here, my domain, if I were going to write this in interval notation, the boundary is included, is equal to. So my domain, the lower boundary is -4. And because it is equal to -4, I use a bracket. But then all the way up to +3. But +3 is not equal to. So I use a parenthesis. For the domain, both end values were equal to, so my lower boundary is -5 and my upper boundary is +5, and the range does include +5. So interval notation is a much more compact way to write intervals. And when we start getting more complicated, like with this increasing, decreasing, so for an increasing interval, I'll do orange. For the increasing intervals, we had multiple locations. So now when this runs off the edge of your graph, it is assumed that that means that it's an arrow and it's going to continue on forever. So in this case, our lower bound of that interval is -infinity. This out here is going to keep going forever and ever in the negative direction. And then it is increasing to this value of 1. And then we are going to want, there is some debate as to whether or not the interval, the function is actually increasing at the end point. Most of the time you see at the end point that it's not increasing and decreasing at the same time there. So usually you see that with an open, with a parenthesis that not equal to, and then we do union, and then it is increasing again from 3 to 5. Those are my x values here, where it is increasing again from 3 to 5, and then union, it is increasing again from 12 on. You cannot equal infinity or -infinity, so you'll never have a bracket at either of the infinities. So that would be the intervals where it is increasing. I'm now going to do the intervals where my graph is decreasing. Well, we saw that it was decreasing from +1 to +3, and then it was decreasing again in this interval. So from 5 to 9. When we talk about intervals of increase and decrease, we are talking over which x values. So this is like the domain of where the function is increasing or decreasing. And then there are no other intervals of decrease. So that is my increasing, then decreasing, and then constant. The function is constant only in this section here. So those x values are from 9 to 12. Now, if I had given you a restricted domain, let's say that we are talking on the interval from, let's go -2 to +13, and I'm going to put an open circle there. So I'm not looking at anything here or anything beyond here. So now instead of having an infinite domain for this graph, I am only looking from -2 to 13. So now the only ones of these that are going to change, my increasing, is the only one that goes outside those boundaries. So now if we are only on this domain, oops, I'm going to do that in green and blue, then our increasing intervals are not going to go from -infinity to +infinity. It's going to go from -2 to 1. 3 to 5 is still inside that. And then 12 is still inside it. But now I'm going to go to 13. And it is an open bracket at the end. It is that parenthesis, not a bracket. Oh, it is closed on the left end because it's filled in circle. The function can equal -2. But with the open circle at 13, that is the end, and the function will not actually equal that. So that is interval notation and increasing and decreasing. So we can, I said it in words, but I want to actually put these definitions in the mathematical definition of a function is increasing on an interval, decreasing on an interval, and constant on an interval. So f of x is increasing on an interval for any x1 and x sub 2. So that's just so that we can tell them apart. So the function is increasing if x1 is less than x2. So that means x1 is to the left of x2. So I am moving, as I go over this interval, I am moving from left to right. If x sub 1 is less than x sub 2, implies that f of x sub 1 is also less than f of x sub 2. So what this means is if I have a graph, x sub 1 and x sub 2, x sub 1 is less than x sub 2, it is increasing if f of x sub 1, oops, I put it in the wrong spot. F of x sub 1 is less than f of x sub 2. So we see that that is increasing. As I move from left to right, the function is increasing. That is the definition of increasing on an interval. And this is true for all values of x on that interval. Then a function is decreasing, again, for any x sub 1 and x sub 2 on the interval, that when I know, oopsie, what is it doing? When I know that x sub 1 is less than x sub 2. So again, that same notation as before, that means I'm moving from left to right. When this implies that f of x sub 1 is greater than f of x sub 2. So once again, I have x sub 1 less than x sub 2, but now f of x sub 1 is greater than f of x sub 2. So I see that that is, as I'm going from left to right on the graph, the function is decreasing. It is moving down the page. And then a function is constant on an interval, again, for any x sub 1 and x sub 2 if x sub 1 is less than x sub 2 implies that f of x sub 1 equals f of x sub 2. So again, x sub 1 less than x sub 2, but their function values are equal. So here that would be a constant function because there is no change, and that is for every x value in that that meet that as you're moving from left to right. Okay, so then now that we understand increasing intervals and decreasing intervals and constant intervals, and we understand notation, interval notation, and we're thinking of domain and range, if you are given a function and asked to find the domain, we are looking at what is referred to as the implied domain. This function is, its domain is everywhere this function is defined. Anywhere the function is undefined, we know that that must not be part of the domain. So we are implying, by stating that it's a function, we are implying that its domain is everywhere this function is defined. So if I ask for the domain, this is one of those issues. Where would this function be undefined? Well, the denominator must not equal 0. So anywhere the denominator is equal to 0, this function will be undefined. So it's defined everywhere the denominator does not equal 0. Now, there are two ways that you can solve this for the domain, okay? What most of you probably would like to do is solve setting x squared equal to 1, and then when I take the square root of both sides, square root of 1 is 1, except for the fact that when I solve by taking the square root of both sides, remember a negative 1 squared would have also gotten me a positive 1. So when we are solving by taking the square root of both sides, we cannot forget that x cannot equal, or these are not equal, plus or minus 1. I have seen so many kids lose points on tests and quizzes because they forget the plus or minus. If you are worried about forgetting the plus or minus, then just factor. X squared minus 1 is a perfect square minus a perfect square. So it means that when I factor it, it is going to factor into x plus 1 and x minus 1. You should have learned this one coming out of Algebra 2. You should not even have to think. If you have a perfect square minus a perfect square, you should be able to factor it, which means x plus 1 would not equal 0, or x minus 1 would not equal 0. And when we solve these equations, if you are still writing minus 1 to both sides or plus 1 to both sides because you have been required to do that all last year, you no longer have to do that. This is pre-calculus. You should be able to add 1 to both sides without having to write it down. Now, if you want to write it down because it's your comfort zone to see all the steps, go ahead. But there are some of you in here that are like, I'm so ready to be done showing all of my steps. I will let you know which steps you are able to skip. So what I see for this function is that the domain is every value except plus or minus 1. So if we are to write this in interval notation, that means these two are excluded from the domain, and every other value on the number line or in our set of real numbers is the function is defined. So my domain here in interval notation, we just start from left to right. My left boundary is going to be negative infinity up to -1, but not including -1. That's this section here. And then this section, because there's a break, this section is now going to be from -1 to +1. And then our last section, we also have to represent from 1 to infinity. What about this function? Now I have two different functions that are affecting our domain. The first one is that I cannot have a negative value underneath the square root. So for this part of my domain, there will be two parts. We know x minus 2 has to be positive or 0. So when I solve this, I know x has to be greater than or equal to 2. The other part of this is that my denominator, x squared minus x minus 6, cannot equal 0. I cannot divide by 0. So now to solve this quadratic, you can either use the quadratic formula, which I would like for you to start moving away from, because this is a simple factoring problem, and you're going to need to have to learn how to factor again, or remember how to factor. So I need two numbers that multiply to make -6 and add to make -1. That will be -3 and +2. So now what this says is x cannot equal +3 or x cannot equal -2. If you cannot make that leap from the factored version to what my solutions will be, then go ahead and take the step where you write that the factor cannot equal 0. So now both of these have to affect our domain. So if I'm looking at my domain, my purple part of this domain is that x has to be greater than +2. So this is the domain for the purple part. Now, it also has to meet the domain for this blue highlighting, which I wrote in black. So now I have -2 and +3. So these are excluded, and the domain here is everything except those two values. So the domain of my entire function has to be where the function is defined always. So it has to be where these two domains overlap. So they overlap from here to here, but not including 3, because 3 is not defined in both of them. And then they overlap from here on out. So my domain, or implied domain, for m of x is going to be from 2 to 3, not including 3, and then from 3 to infinity. So that would be the domain just where they overlap. Okay, so relative extrema. The word extrema here should make you think of extreme values. But so we want extreme values, maximums or minimums, a lower bound or an upper bound, or the highest value a function can take on and the lowest value a function can take on. But this relative means that we are only looking for extreme values relative to the points near them. So if we are looking for a relative maximum, we are looking at the highest value, not over the entire function, just in the neighborhood of that highest value. So if I look at the -3, 2, it is the 2 is the function maximum value relative to the x values near -3. So f of -3 equals 2 is my relative max. Is there another relative max? Yes, there is another relative max. Relative to the x values near 2, 2 comma 1, or f of 2 equals 1. We're going to write it using function notation because this is those are technically the relative maximum numbers, but we want to say where it happens. So I expect to see this written in function notation. Those are the two maximum function values relative to the other function values around it. So looking at the x values on either side, which of those, where is the highest or largest x value? Relative minimum is going to be the same idea, but now we want the lowest value relative to the function or to the values around it. So my relative min here is going to be f of -1 equals -3, because -3 is the minimum y value related to the points near that point. There is another. So f of 4 equals -1. Don't make a rule. It just so happens that the positive function values were maximums and the negative function values were minimums, but that's not always going to be the case. It is possible that you could have a relative maximum that is a negative function value, and you could have a relative minimum that is a positive function value. Okay, so if I had, if my graph was changed, and I moved my axes, so these points are changing. Those are not going to be. If I change this, so this is no longer the x and y axis, and now my x and y axis are here and here. Now my relative minimums would also be positive numbers because this y value is now above the x axis, as so is this one. So don't make rules like, oh, negative numbers are relative minimums and positive numbers are relative maximums. Not true, okay? So we want to, I've got 2 more things to show you and then we will be done. You are going to be able to use your graphing calculator to approximate a relative max and a relative min. So what I want to show you is how we are going to do that. So let me get back to when you're on the main screen, you're going to hit the y equals button. And then here, if we're going to approximate it, my y1 is highlighted. So I'm going to take my x. So I use that x comma t comma theta comma n, x to the third, and get out of the exponent, minus 4x squared plus x plus 3. And then what I want to do is I want to graph this Oh, I can't see all of the graph. I probably should change my window, or the first thing you can do is you can zoom to 6 and that will make it fit in the screen. Can I see? Is my window big enough that I can see the relative maximum and relative minimum? Now, what I'm going to do is I'm going to let my calculator approximate this for me. Okay, so the way I'm going to do that is I am going to hit above the trace button in blue, it says calc. So I'm going to go second calc, and I want to calculate a relative maximum. So that is option 4. I can take my cursor down and hit enter at 4, or I can just type in 4. And now I need to be to the left of where I think the maximum is. So my cursor is clearly to the left. I hit enter, and now it says right bound. So I want to move my cursor to where I am to the right side of that. And then it asks me if I want to guess. I don't care. I'm doing this so that I don't have to guess. Just go ahead and hit enter again, and it will tell you the relative maximum value for this function. At x equals 0.1314838, the maximum value is 3.0646049. Now, you need to give me at least 3 decimal places. So we had a graph that looked like this, and it did something here. Oops, it turned around. I did it worse. And then it goes down a little bit and then back up. So I used my calculator. So I did second trace, which gets me the calc option. For the left bound, you move the cursor to the left and then hit enter. Okay, and then for the right bound, again, you're going to move the cursor this time to the right of that maximum or minimum, and then you're going to hit enter. It asks you if you want to guess. You just hit enter, and then we're going to write the function. So this was f of, and now I go back and I want to give at least 3 decimal places, rounded or truncated. So either, in this case, both of them would be the same. 1.3 or 0.131, it would be if I rounded, and then if I just truncated and ignored the end. So 0.131 was the x value, and my y value was 3.064 if I truncate, 3.065 if I round. And this was my relative max, and I approximated it because these are rounded or truncated answers. And now I'm going to do the same thing to find the relative min. So I'm going to go second calc, and this time I select minimum. I can either scroll down to 3 or I can hit 3, and I now want to find the minimum, so I need to be to the left of that minimum, and then I need to move until the cursor is to the right of the minimum. Hit enter when it asks to guess, and my minimum, approximate relative minimum, is f of 2.535 is equal to negative 3.879. So when I do f of, now I've already forgotten the numbers, 2.535 equals negative, was it 3.879 is my relative minimum or relative min. You can abbreviate that to relative max or relative min. You could actually abbreviate it to REL period MAX, but do not reduce or don't shorten it any more than that. So I can use my calculator to approximate the relative max and the relative min on my graph. The last thing I want to show you is, I'm going to change my background so that I can graph this one easier. I want to graph my piecewise defined function. So I'm going to make my axes. What this means is that one equation is not able to define the entire function. So we need multiple functions to define it. So when I set up my scale, I'm going to count by each unit is, I'm going to count by ones in the y direction, but I'm going to count by 1/2 in the x direction, just because it makes it easier to count off the slope. So this function is only defined for values of x less than -1. So from here, from here this way is only the part of that graph that I'm going to graph. This one goes from -1 to +2. So in this interval, I'm just going to graph part of that x squared function. This one is 1/2 x plus 1. So now for this last one, everything beyond 2 is going to be graphed with 2x plus 1. So you can recognize the parent functions, or you can plot points. I know that my y-intercept here would be at +1, which I'm not going to actually plot it there. And then if I have a slope of 1/2, to go backwards, I would go down 1 and to the left. Oh, down 1. I went down 2 because I changed my scale. Down 1 and to the left 2. So at -1, I should have an open circle at 1/2. I could also determine that by plugging in -1 into that. And I plug in -1, I get -1/2 plus 1. So that's an open circle because it is not equal to, and then it's just going to be a line. So I go down 1 to the left 2, down 1 to the left 2. Remember, I'm only going down half on my scale because my scale in the y direction counts by 2. So now this part of my graph just does that, because it is the line only up to x equals -1, and then the function has to be defined by a different function. And both of these are filled in circles on each side because what I see is or equal to or equal to. So now I'm going to be graphing the x squared function. -1 squared is 1. 0 squared is 0. 1 squared is 1. And 2 squared is 4. So those are those parts of my parabola that I am graphing, only up to the 2, because after the 2, this function is defined by another function, which is 2x plus 1. So when I plug in 2, I should be at 5. This would be at 7, 3, I would be at 4, 5, 6, 7. And then from here, this should be an open circle. So this should be an open circle and then there. All right.